Alright, class, today we are going to talk about section 5.2, which is on definite integrals. And this basically starts where we left off last time. That question of, well, if we continue to increase the number of rectangles we have without bound, will we end up getting the actual area? So that is where we're going to start. Basically, let's say I have this function, I don't know, f of x, maybe it looks like this. Okay. And let's say I want to find the area between the graph of f and the x-axis between A and B. So basically, we want to find this. Okay. So essentially what we do is we split this region, or we are going to use Riemann sums, and I was remiss last time in not calling them by their real name. Those estimates are called Riemann sums. Okay, but we're going to use Riemann sums. Okay, spelled like this, named after the mathematician, to approximate this area. Okay. Using n rectangles. Okay, so we are going to split this interval a to b into n pieces. Okay, so I'm going to make this n rectangles. Okay, and so we are going to end up with, lots of rectangles here. Here I'm making, say, a left-handed estimate. For example. Okay, and so on and so forth. All right, and so basically, if we want to add up all these areas, if I have n rectangles, first I need the height. So I'm going to call each one of these tick marks that I've labeled off, I'm going to start labeling them. We're going to start at 0, okay, where x sub 0 is a, and then this next one is x1, x2, x3, so on, all the way up to, this would be x to the n minus 1, this would be x to the n, oops, that's n minus 2, n minus 1, and here's x to the n at b. Okay. So, and then for each x I actually have an f value that's associated with it, right? Here is f of a, which is f of x0. Here's f of x1. Here's f of x2, and so on. And then this would be f of x to x, not to the n, but f of xn, f of xn minus 1, etc. Okay? So these are going to make up the heights. All right, so we'll have the heights as we go along here. That will all come, whether we use a left-handed estimate or right-handed estimate, all that does is change whether we use f of x naught or f of xn. That's really the only big difference there. What we really need to know now is where we get the base from. So I'm going to call the base, well, it's going to be our step size, delta x. Right? That's going to be our change in x. And we're splitting this into even rectangles. So I'm going to say with equal bases. Okay, we don't want to mess with this whole different base sizes or whatnot. Okay, that is a good way to go, depending on how you do it. But for this process, we're not going to. And if we're breaking each, say this region A to B in equal subintervals, that step size is simply going to be, well, delta x is going to be, well, I'll take the interval b minus a, the length of the interval, which is b minus a, and divide it by n. Okay, that's how you could get the length of all these things. All right? So, if I wanted the net area, okay, so the net area, if you can see all that still, right, is going to be approximately all this stuff added together, right? So it will be, say if I'm doing a, let's do a left-handed estimate to start with, right? Because that's going to be all of my heights, so that's f of x naught plus f of x1 plus all the way up to f of x to the n minus 1 times the heights, which, or excuse me, times the base, which is delta x. Okay, and the net area is also approximately equal to the right-handed estimate, or the right-handed Riemann sum, which just the same thing, it just starts at x1. So this will be f of x1 plus f of x2, so on all the way up to f of x in delta x. Okay. Now I want to simplify this notation a little bit. So what I want to do is introduce what is called sigma notation. All right, sigma notation. You may have seen it before. And this camera really does not want to focus right now. Okay. Sigma notation, basically, it's a big capital sigma, and it basically just means you're summing things up. So it has an index. If I give it, say, k equals 1 to 5, let's say, and I'm summing up k, this says that I'm going to sum up k from 1 to 5. Okay, so k going from 1 to 5 would be 1, 2, 3, 4, 5, but the sigma notation tells me I'm just going to put a plus sign between everything. Okay, so that would be that added up, and if you were to do that, I believe you get 15 out. Okay, that doesn't really matter. What really matters is that I'm going to incorporate this notation, basically to simplify things, so I'm not writing it like this all the time. Okay, so with this notation, the left-handed estimate is going to be the sum. Okay, k is going to be going from 0 to n minus 1, right, because I'm summing things up from 0 to n minus 1 of these f's. So these f's of xk's. Okay, and then we're multiplying by delta x. And then the right-handed sum, right? Well, that's going to be going from k equals 1 to n, right? It goes from 1 to n of these f of xk's delta x. So this is a much more compact way to do this. And basically, what we have is the net area is approximately equal to both of these, and these are also very close to each other, right? These get closer and closer to each other the higher n gets, right? The more rectangles we use, the closer L and R get. So with the more rectangles, the closer The left-handed estimate is to the right-handed estimate. Okay? So what we're basically going to do is look at these expressions, and we're going to have to take my word on some of this. We're not going to prove anything, but we're basically going to let the number of rectangles go to infinity. And when we do that, as we increase the number of rectangles, what happens to the bases? Well, the bases start getting smaller and smaller. So this should be reminiscent of when we found the derivative. We took secant lines, remember, and did then let the interval shrink down to 0, and we get the tangent line. We're doing the same thing now. We're taking areas of rectangles and letting them shift down to 0. And like I mentioned before, when you do that, you're looking at things, you're basically just cramming a bunch of lines on top of each other to fill in this area as you go along. Okay? So what we're going to do is, the idea is we let that number of rectangles go to infinity, right? Remember, this is the number of rectangles. N for number. All right, so here's the proposition. Here's the proposition. I'm calling it a proposition because I'm not going to prove it. Okay, is basically that the net area between f of x and the x-axis is actually equal to, okay, the limit as n goes to infinity of this sum here, k going from 0 to n minus 1, f of x to the k delta x, okay, which is also going to be equal to the limit as n goes to infinity of the right-handed sum, which is k going from 1 to n of x, f of x to the k delta x. And you'll study this a little bit more in Cal 2, but basically what has happened is when we let n go to infinity, we actually get equality, the approximately equal to, okay, the approximately equal to becomes actual equality. We get full-on equal signs. Okay, so a simpler way to write this is we just do the sum of k going from 0 to infinity, f of x to the k delta x. Okay, and we also said that that's equal to the right-handed sum, so k going from 1 to infinity, f of x sub k delta x. Now, when n goes to infinity, here's the final step, delta x. Well, delta x, remember, is b minus a to the n. And so this is just some constant, but the denominator is going to infinity, so where does this thing go? Well, it goes to 0. So we basically have a delta x going to 0, and what that is a dx. Remember, dx is your delta x when it gets very, very small. Not always, but in this abstract sense, consider it that way. So what this ends up equaling, okay, is we have a new formula that both of these become equal to the integral. And there's where that integral sign comes from. It comes from sum, right? It's a special kind of infinite sum. Okay, so it's the integral from a to b, so we give it limits. That means it's a definite integral. Okay, f of x dx. Okay, so essentially what we're doing, if you think about this, okay, as we let the number of rectangles go to infinity, the length of the bases go to 0, and what we're essentially doing when that happens is we are adding up every point from here to here. Every single one gets added together. Okay? And then we multiply them by delta x, but that's shrinking to 0. So what we essentially have here is this is an infinite thing, right? We're adding together, because there's an infinite number of points from here to here. We add them all together. That should be infinite, right? But we're multiplying that whole time by something that's going to 0 at the same time. So we have a piece that's going to infinity and a piece that's going to 0. And as you saw with a couple of examples in L'Hopital's rule, that happens all the time and often gives you a number. And what this actually gives you is the net area. All right, so this is the net area between f of x and the x-axis. So this is essentially, you're summing up all x values. Or excuse me, all f of x values between f of a and f of b. Okay, and multiplying by delta x, and just kind of shrinking it in there, as delta x goes to 0. So essentially, this may very well be one of the most difficult things you've ever seen in a math course. I mean, what we're essentially saying is that we're adding an infinite number of things together and then multiplying that by a thing that's shrinking. So we can't actually, well, I won't say it like that. We can't find these by hand, these integrals. Okay. But we'll get to that a little later. At least we can't find them the long way, how you might expect. Okay, so what we have is the net area. Okay, between f of x on the interval a to b, oops, sorry, between f of x and the x-axis. On the interval a to b is the definite integral, that's what we call it, from a to b, f of x dx. Okay. All right, so that's what we call this. This is the definite integral of f of x on the interval a to b. Okay. Now you may be wondering, well, this uses the same notation, the same symbols as the antiderivative. Okay, so that's one thing to notice, is we notice that this uses the same notation as antiderivatives. And we give it the same name, integral. Okay? And the reason, there's a reason for that, okay? That's not by accident, okay? Which means that this area is very closely related to the antiderivative. And you could probably already guess that, because remember, before, last section, we were looking at velocities and using the areas to map them back to position, right? So remember last time, we were taking velocity and using the area to get back to position, essentially, right? And what we've just, and that's technically, right, the antiderivative, going from velocity to position. Okay? Right? So these are very closely related. That's what we'll be talking about next time, is how they're related. But what we're talking about in this section, for the most part, okay, the majority of this lecture is on the definite integral as an area. Okay, so here we go. Let's say the one property I want to give here is, well, let's do a very quick example, kind of like how we did last time. Let's say this is the velocity, v of t, is, say, 50 miles per hour, and we're going for 2 hours. Okay, and we know that this area here is going to be 100, right? So I know the net area is going to be 50 times 2, so that's 50 miles per hour, times 2 hours, which is 100 miles. Okay, so what I'm basically saying with it being the area, as a simple example, is that the definite integral from 0 to 2, right, we're talking 0 to 2, of v of t, okay, is 100. Right, that's essentially what we're saying. All right, but from that point, when we have normal areas, right, if, let's say I have the area of, let's say I have this shape here. Okay, I'll pretend I drew that right. I have this crazy shape here, and I want to find the area of it. Now, there is no formula out there for the area of this particular shape, right? That just doesn't exist. But what we do instead is, let's pretend that's going straight down, is break this up into manageable pieces, okay, and say that this is 0, A, B, C, D, okay, and I would maybe find the area of this rectangle, then find the area of this rectangle, find the area of this rectangle, and then this triangle, and the area of the full region is, well, you just add them up. A1 plus A2 plus A3 plus A4, and there you go. We can do the same thing for integrals. Okay, so the integral property that we have, so we can do the same for integrals. Okay, so here's, let's just write it out. If I was doing the integral from 0 to d of f of x, let's say that this guy was f of x, and pretend that these lines aren't part of the graph, it's just jumps. Okay. All right. Now, if I was doing this integral from 0 to d, I could instead take the net areas of each shaded piece instead, and it would be, say, the integral from 0 to a of f of x dx plus the integral from a to b of f of x dx plus the integral from b to c of f of x dx plus, let me fit it in here, plus the integral from c to d of f of x dx. Okay? Now, I didn't put numbers in here, but you could calculate these by hand if you wanted to, if you were given numbers, just easy areas of rectangles and triangles there. But this is basically the rule that the book gives you. Okay, and this is how it gives it to you. It will say, if A is less than or equal to B is less than or equal to C, then the integral from A to C of f of x dx is equal to A to B of f of x dx plus B to C of f of x dx. Okay, which, just looking at that in words, I don't think is really all that enlightening. But if you just think about it like this with the picture, or here I could draw another picture and say, oh, I have this area from A to B, and then I have this area from B to C. Okay? And a very useful thing is you can actually move things around. So if you have the integral from A to C is equal to integral from A to B plus the integral from B to C, but if you were to move this over, you would have, kind of lose that because of the way I drew this, but you would have, let's move this guy over. You could say that the integral from A to B is equal to, oops, is equal to the integral from A to C of f of x dx minus the integral from B to C of f of x dx. And what does this mean? Well, let's say we knew what the area of this entire region was. Okay? But I want to know specifically what this area is. So if I do that, well, I take the area of the full region, okay, and then subtract the area from B to C. So I just take that out, and that gives me the area from A to B. Okay, so area of the full region, subtract out the area of what you have. And I often, sometimes it's very helpful to go, you can draw this with blocks and number lines and stuff, and it tends to help me. I'm very much a visual learner, so I tend to like to visualize everything. But so if you're looking for some integral and you want to, and you're given information about it, okay, then you can use some of these properties. But again, you can always say draw a little picture. It might not be an accurate picture, but it's still helpful. Okay, a common question you'll see, it's a very common calculus question. Say we're given a graph, okay, and we're told that the total area of each region is given in the graph below. So we want to evaluate the integral. So what that means is that we are told the total area of these shaded regions between the graph of f of x and the x-axis. So between f and the x-axis, what that means is, well, here it's this upper region, but down here it's, you know, here. Okay, so a lot of people will kind of simplify and try to say the area below the curve, but below the curve down here, well, that could be all sorts of things. Okay, so it's the area between the graph and the axis. And each region here, we are given the total area. So when we go to integrate, let's say I want to find the integral. Let's start up here. Let's say I want to find the integral from 0 to 3 of f of x dx. The integral from 0 to 3, that's going to be this area here. That's, of course, going to be 10. All right. But people tend to start having trouble when they say, let's do the integral from 0 to 5 of f of x dx. Okay, 0 to 5, so that's 0 to 5. Well, it's basically going to be this area plus this one. But remember, this gives net area. So remember, where can I put this? Over here. Remember, the integral from a to b of f of x dx gives net area, whereas these numbers that we're given here are total areas. Okay, so they're all going to be positive. All right, so I'm going to go ahead and write out my rules. This would be the integral from 0 to 3 of f of x dx. All right, I could do 0 to 3, and the integral from 3 to 5 f of x dx. Okay, so that is going to be, let me move this over here, that is going to be 10 minus 8, which will be 2. Okay. All right. Now let's erase this and start writing down here. Let's say I want the integral from 0 to 6 f of x dx. Okay. Well, that's going to be the integral from 0 to 3. Okay. F of x dx. Okay, and I don't want to crash into my graph there, but then it will be plus the integral from 3 to 5 of f of x dx plus the integral from 5 to 6 f of x dx. Okay. So 0 to 3 is 10, 3 to 5 is minus 8 because it's below the x-axis, then 5 to 6 is plus 4. So that integral is going to end up being, well, 10 minus 8, which is 2, plus 4, which is 6. So you really could just do, another way you could do this is if you were looking for the integral from 0 to 6 of f of x dx, you could do the integral from 0 to 5 of f of x dx, which we just found in our previous problem, 0 to 5, and then plus the next piece, 5 to 6. Right, so 0 to 5 we found was 2, 5 to 6 is plus 4, so that's 6. All right, that's where this is useful, is that we can split it up in any way that we find helpful to us solving these problems. And from here, you can probably see that this is pretty simple. You can probably just look at it now and tell me what the integral from 0 to, I didn't give this a number here, let's say that's 7. Okay. Just looking at it, what will be the integral from 0 to 7? Well, it's going to be 10 minus 8 plus 4 minus 1, end up being 5. Okay, no problem. All right, maybe we can look at another one. They don't all start at 0, for example. We could start one integral at, let's say I want to integrate, let's say 3 to 6 f of x dx. Well, 3 to 6, that will be negative 8, okay, plus 4. So negative 4. Okay. So what a positive value means for an integral is that the function spends most of its life above the x-axis, where a negative number means it spends most of its life in that region below. So here, from 3 to 6, there's more of this function below the axis than above. So it will end up with a negative. Right? How about the integral from, let's say, 5 to 7 of f of x dx? Well, 5 to 7, that'll be 4 minus 1, which is 3. Okay? So a lot of the problems you'll see in this section are this. It'll give you a graph of these regions, or it will be given a graph like this, where you could calculate the area of each region using basic geometry. And, you'd go from there and calculate the values. Now, what happens, let's say, if you don't have a graph? Okay, so let's say that we have that the integral from 0 to 4 is f of x dx is equal to 2, and that the integral from 0 to 6 of f of x dx is equal to negative 4. And we want to find the integral from 0 to 6, the integral from 4 to 6, the integral, well, and I should say integral from 0 to 6 of 2 times f of x dx, the integral from 4 to 0, and the integral from 6 to 0 of 8 f of x dx. Okay, so we'll start with 0 to 6 of 2 f of x dx. So we'll start that here. Okay. So basically what this example is going to show is that you can move constants outside like you do with derivatives. We have the same integral rule. I mean, we talked about that, I believe, in the antiderivative section. The same rule holds here. So this is same constant rule we've always had. Okay, which is that we can bring that 2 outside, so that will be 2 times the integral from 0 to 6 of f of x dx. Okay, and that we know 0 to 6 is negative 4. So that's just going to be 2 times negative 4, which is negative 8. And yes, I want you to write this step, okay, for now. Eventually you can jump to here, but I really want to see the rules when you're doing this. Don't just, mess around with the numbers until you get something out eventually. I actually want to see you applying the rules. So yeah, it's tedious, but just do it. Okay, the next thing I actually want to focus on is not 4 to 6. I want to focus on these two for a second. Let me go ahead and erase this. What I don't understand, your book, for some reason, does these opposite order things without a good way to really explain why it works this way. This is explained a lot better in the next section, but since your book is going to ask you questions about it and all that, we might as well go ahead and talk about it now, and I can just explain it next time. When you go from 4 to 0, okay, 4 to 0, if you go out of order, it's basically the negative of going in order. Okay, so an out of order integral is a negative of the in order integral. Okay, so that's just going to be 0 to 4 was 2, so this is just going to be negative 2. I'll put that in parentheses just so it's clear. So let me just write that, an out of order integral is negative. Now, well, it's negative of the in order. But as long as you remember that, that it's just negative. And you'll do that a lot, in Cal 2 especially, that trick shows up all the time. Because often when you get formulas, when you're dealing with various things, you actually end up with a negative or an out of order integral, and you want it in order. It's just usually easier to deal with in order. And you just, when you do that, you flip it, negate it, what have you. This means you can flip integrals all you want as long as you negate them as well. Basically, if you flip this thing, you have to flip the sign. Simple as that. So, when we do 6 to 0 of 8 times f of x dx, okay, we're going to use two rules. We're going to take the 8 out, and then when we flip it from 0 to 6, we're going to negate it, okay, to get f of x dx. All right, and so that's just going to be negative 8 times, and what was the integral of 0 to 6? That was negative 4. Okay. Oh, sorry about that. Camera issues. I don't know what happened there. Just kind of shut off for some reason. Anyway, which is 32. Sorry about that. But anyway, yeah, so for these things, I want you to actually write out a step with the rules, just so we get it. Now, the trickier one here is going to be 4 to 6, and that's the one I really want to talk about. So let me set this up so that's all you see here. Okay, so if I want to find the integral from 4 to 6, and I have the integral from 0 to 4 and from 0 to 6, well, here's what we're going to do. We're going to use that property that we mentioned before, basically this one, okay, this property. But I don't think this really means much to students when they're first learning this. What we're essentially going to do is we have some sort of integral thing going on. We've got, I'm going to just draw it with some boxes here. I've got the integral from 0 to 4, which I know from here is 2. Okay, and then I also know that the integral from 0 to 6, so the whole integral is negative 4. So I need some things beneath, right? Because the whole thing, the whole area, net area I should say, is negative 4. So if the area from 0 to 4 is 2, and the area from 0 to 6, the whole shebang, is negative 4, what must this area in here be? Okay. Well, you can just kind of look at it and see that it should probably be negative 6, right? Possibly, because right, the integral from 0 to 6 needs to be negative 4, and we already have 2 up here, so we got to get negative 4, and negative 6 is probably it. What rule we're basically using here is this one, okay? But what you can do is you can say, well, I know that 0 to 6 of f of x dx is equal to 0 to 4 of f of x dx plus 4 to 6 of f of x dx. So this is what we're looking for, and then we have these two things here. Okay. So this thing, 0 to 6, I know is negative 4. 0 to 4 I know is 2, and this 4 to 6 integral is what I'm actually looking for. And then if I were to move this 2 over, I get negative 6 is equal to this integral from 4 to 6 of f of x dx, which is exactly what we established using this. Okay? So basically this integral is -6. That's the answer. Now another way you can do this is the other part of this rule is the full integral minus one of your pieces is equal to the other piece. All right, so the full integral, 0 to 6, the one that covers everything, of f of x dx, minus, okay, now the other one we had was 0 to 4, right? If we subtract out 0 to 4, we're actually given 4 to 6. So here's 0 to 6, now we're subtracting out 0 to 4, and that gives us 4 to 6, which is what we have right here. And if we fill in those pieces, 0 to 6 was -4, minus 0 to 4, which was 2, which is -6. Okay? I know you'll want to just do the picture and let that be all your work, but you really do need to write some of these formulas, because if you don't, expect to see them, you need to write them, okay? Because you need practice with these. You need practice with splitting these things up. You need practice with the differences and the sums and whatnot, okay? Now, there's one final rule I want to talk about before I do some more examples concerning this. Okay, here's the property. It basically boils down to even and odd functions. So if a function is even, then the integral from -a to a of f of x dx is 2 times the integral from 0 to a. So where this comes from is if you consider an even function would be something like, this would be maybe 16 minus x squared. Okay. Even is symmetric about the y-axis. Okay. And basically what that means is that if it's symmetric, that means this side is exactly the same as this side. So if this is, let's see, -a to a, then the integral from -a to a, the full area, is going to be 2 times this area. So you could really just calculate this and multiply it by 2. Another way of saying this rule is that the integral from -a to a of f of x dx, oops, let me do it this way, -a to 0 of f of x dx is equal to 0 to a of f of x dx. That they match on either side. Okay. On the other hand, if a function is odd, that means you're symmetric about the origin. Okay, a very famous odd function would be x cubed. Okay. Now, if you integrate from, say, -a to a, well, what happens is that this region is exactly the same as this region, but one's on, above the axis, one's below the axis. So that means that this, whatever area it is going to cancel this one out. So whatever the area is, this is the negative of it. Okay, so actually let me make that so that's a little clearer. This area is negative that area. Okay, so another way to write this would be that -a to 0 of f of x dx is equal to negative of 0 to a of f of x dx. Okay, now where this is helpful is without even knowing the stuff in the next section, if I know a function is odd, say I'm doing the integral from -1 to 1 of x cubed dx, I already know it's 0, right? Since x cubed is odd. right? Another thing I can do is, let's say, the integral from negative 100 to 100 of sine x dx. Well, I know sine is odd, so I know that that's 0. Okay? And it's one of those things, if you don't know this, it's not necessarily going to kill you, but it can actually help. You'll see it a lot in Cal 2 as well, because say I know x squared is even, so instead of integrating maybe negative 2 to 2 of x squared dx, I could instead just find the integral from 0 to 2 of x squared dx. And that's actually easier to do, we'll see in the next section. Okay, but this is just a really useful trick that's going to help us help you speed things along as you decide to calculate integrals. Now we can also deal with the integral rules and whatnot as follows, incorporating this. Okay, so let's say I know that f of x is odd, and I know the integral from 1 to 2 of f of x dx is equal to 3. All right, then I want to find the integral from negative 1 to 2 of f of x dx. Okay, so how are we going to do this? Well, if we go to our graph, or a graph, okay, let's just consider a graph. It doesn't really matter what it looks like. The piece I know is the integral from 1 to 2. Okay, so let's say it's, I don't know, this rectangle right here. Okay, and I know that that's 3. Now I don't know if that's what this guy really looks like. It doesn't matter, I just need a graphical representation. Now I want the integral from negative 1 to 2, so I want to be able to find negative 1 to 2. Okay, now the only thing I know about this guy is that it's odd. Okay, so what that means is that no matter what happens over here, it's symmetric over here. So if and odd functions have to cross 0, 0 because they're symmetric about the origin. So no matter what shape I do, it doesn't really matter. Let's say the graph looks like this. Well, it has to also look like this on this side. I know that whatever this guy is, say from 0 to 1 is a, I know negative 1 to 0 has to be negative a. Okay, so I know, or I'll say we know, that the integral from negative 1 to 1 of f of x dx is 0. Okay, so basically this whole area thing, right, from negative 1 to 2 is going to be, I'm going to break it into the pieces I have. What pieces do I have? I have 1 to 2, and I have negative 1 to 1. So negative 1 to 2 I can break up as negative 1 to 1 f of x dx plus 1 to 2 of f of x dx, which is, okay, negative 1 to 1 I know is 0, 1 to 2 I know is 3, so it comes out to be 3. Now, of course, you probably realize that from here. Okay. But again, you need to write a statement like this using the properties. Right? The whole point of this is not graphical manipulation. It's giving you practice with these properties. That's the whole point of this section. All right? That's the whole point of all this. So that's really what I want to, make sure you get a handle on. All right, let's look at another example. Let's say here f of x is even this time, so it's a little different. And I know the integral from 0 to 1 of f of x dx is 2, and the integral from 1 to 5 of f of x dx is 6. All right, so I want to find the integral from negative 1 to 5. All right, so let's take a look at what we already have here. I always like to give a little graph. I know 0 to 1 is 2, right? So I know the area of that region is 2. And then I know the area of the region from, let's say, from 1 to 5 is 6, right? These are the things I'm told. 0 to 1 is 2, 1 to 5 is 6. I'm just kind of drawing whatever. It doesn't really matter what they look like. But what I want, right, what do we want? We want the integral from -1 to 5. So I'm missing a piece here, right? Now, which is it going to be? Well, if f were odd, like the last time, we'd put a piece right here that would match this exactly, right? But it's not odd, it's even. So even means we put a piece here. Okay. So that means the integral from -1 to 5 is going to be 4 plus 6, which is going to be 10. Now this comes from the fact that f is even. All right, but if I want to write this with properties, right? How do we write this with properties? It's good to know what's going on graphically, but properties is what's important because you can't always draw a picture, right? It takes too long. You have to get familiar with these rules eventually. What we basically do is we go to our even and odd statement. Okay, and what did it say? It said that if a function's even, then this is true with the integral. Okay, so that means we have 0 to 1, but the integral from -1 to 1, so integral from -1 to 1 of f of x dx is going to be 2 times the integral from 0 to 1 of f of x dx. Okay, which we have up here is 2, so this is 2 times 2, which is 4, which is what we got just by thinking about it here. But again, knowing this property is what's important here, because when we go to real functions, right, and we're doing this analytically, we're doing it by hand, we need to just know these rules. So anyway, then I'm going to use the split up property, that -1 to 5. I can write with the other two pieces I have. I have -1 to 1, right, that piece of f of x dx, plus 1 to 5 f of x dx. And this is what's really important. Okay, splitting that up. So I know that this piece is 4, and I know that this piece is 6, which comes out to be 10. Okay, so that is that essentially. You'll have a couple of problems to help with this. One, or hopefully help practicing this. One little thing I wanted to mention before we finally finish this off is that if you're given a graph like this, and this is 10, this is 8, this is 2, okay, and let's say this is who cares, this is 5 here, right? So we know that the integral from 0 to 5 f of x dx, right, is the net area. I meant to mention this before the graph but forgot. So that's going to be 10 minus 8, which is going to be 2 plus 2, which is 4. But if I wanted the total area, right, the total area in the book will ask for this. It will be the absolute value of f of x dx. Okay, and what that essentially does is anything that's below the x-axis, the absolute value brings it up above the x-axis. So the absolute value of f of x is here in this piece. And I'm just bringing this up because this shows up quite a bit in Cal 2, especially early Cal 2, when you're looking at total distance traveled, right? So, so total area would be 10 plus 8 plus 2, okay, which would be 20, Right, so be very careful with which one they're asking for. Absolute value, which is total area, or non-absolute value, which is net area and incorporates negatives.